So welcome to 13th talk of the higher categories trading seminar. Today's speaker is Grigory from University of Toronto and High School of Economics, and he'll be talking about categories. Categories fibered in infinity group parts. That is basically the fourth chapter of Cisinski. So Grigory, take it away.
Okay, thank you. Thank you for allowing me to speak here. Okay, so basically what we're trying to do here is we're trying to generalize the following construction from ordinary category theory. So let me write down. Let me write down the title of the talk. By the way, is my handwriting intelligible, or should I maybe switch to some other pen?
Yeah, I think you're fine.
Okay, great. Okay, so what is the setup? So assume that we have a small category C, and then we have fully faithful embedding of a pre-sheaf category of C, well, pre-sheafs of sets, of course, into an over category of C inside of all small categories. So how it's done? Well, assume that we have a pre-sheaf F. Then we can consider a category of elements a category of elements of F, which comes equipped with a canonical map into the initial category C. And thus we get a functor which goes from category of pre-sheaves into an over category of C, which maps a pre-sheaf into its category of elements together with its canonical map into C. And this functor admits both left and right adjoins, and it is relatively easy to describe a left adjoint of this functor. So assume that we have some over category I, and then the left adjoint will be just the colimit of the composite functor. So we take the composite functor of this phi and the unit embedding H, and we take a colimit of H phi, and we obtain a left adjoint of, well, I didn't really denote it by anything. Let's denote it by L, L phi. Yeah, so now let's describe the right adjoint of this functor. So assume that once again we have some category over C, and what is the value of the right adjoint on this category? Well, let's denote it maybe by R. Then R of phi from I to C on an object C inside of category C curly is a set of functors from this common category of C small into I, such that phi u from this common category into C is the canonical projection. the forgetful functor, whatever you want to call it. Okay, so we have a way to think of pre-sheaves on a category as a full subcategory of this common category cat over C. And we want to do something similar for infinity categories and more generally just for simplicial sets. To do this, we want to characterize an essential image of this functor L, which was described earlier, and let's do this. So the categories over C, which have the form of categories of elements, are characterized by the following properties. So these are the functors E from X to C, such that for any object X small inside of X, if we define C small to be P of X, the induced functor X over X to C over C is an isomorphism. Okay, so now we know that the nerve functor applied to small categories, to a functor between small categories, gives an inner fibration of simplicial sets. And so we have the following nice proposition. It is proposition 412 in Cisinski, which states that a morphism of simplicial sets is a right fibration if and only if P is inner fibration such that for any object X small inside of X, if we put C to be P of X, and the induced functor from X over X small to C over C is a trivial fibration. So let's prove this. First, observe that we can identify the nth form with a join of a boundary of n-1 simplex with a point. And yeah, for n greater than 0, obviously. And then we can apply a result from section 3. So lemma 3420, but well, this was previously discussed, I believe, to reformulate the following Lifton problem. So we have a Lifton problem like this. And by this result on joins, we can reformulate it as a Lifton problem like this. with additional requirement that u of n equals x. So after this reformulation, we observe that the class of rate vibrations is characterizable as class of inner vibrations plus the rate lifting property with respect to all inclusions of the nth horn into n simplex, and this proves the proposition because we found an equivalent formulation of triviality of this vibration, which is stated here in terms of this lifting problem, which has a solution for rate vibrations. Okay. So, yeah, so we have this result. And now we have a corollary of this proposition. Which states that the nerve of any Rothendick vibration with discrete fibers between small categories is in fact a rate vibration. So let's also prove this. We have a canonical identification, and C over X is isomorphic to the nerve of this common category, and now we can apply the previous proposition to the characterization of Rothendick vibrations special type. Okay, so I'm not sure that this was really illuminating, but let's move on. Okay, so now we want to describe a model structure on an over category of, on common category of simplicial sets over an arbitrary simplicial set called contravariant model category structure over C. So assume that C is some simplicial set and denote by P of C is a full subcategory of this over category with objects being the right vibrations of the form EF from F to C. And objects of this category are called right fibrant over C. Yes. So now if we have a morphism from F to G over C, so this is a morphism in this category of right fibrant objects over C. We say that this morphism F is a fiberwise equivalence if for any object C small and C, the induced map on fibers is an equivalence of infinity group weights. So white is an infinity group weight. Well, FC obviously can be defined as a pullback of this structure map along a map from a point corresponding to C. And since this thing here is a right fibration, it follows by Grigory 2.5.6 that the fiber of this right fibration is in fact an infinity group weight. Okay, so now we arrive to the following theorem due to Royal, which describes this model category structure that I was speaking about, which appears on this over category of C. So there is a unique model category structure in the category of simplicial sets over C with cofibrations coinciding with monomorphisms in this category, and with fibrant objects being the right fibrations of well, the right fibrant objects right fibrant objects over C. And additionally, the class of vibrations between right vibrant objects coincides with the class of right vibrations. So first, we need some additional results to prove this theorem. And first thing that we observe is that, in fact, if we take our simplicial set C to be just a point, then the contravariant model structure coincides with the Kahn-Quillen model structure on simplicial sets. So observation, if C is a point, then contravariant model structure, just the Kahn-Quillen model structure. And this can be, in fact, generalized. So if C is, in fact, an infinity groupoid, then contravariant model structure is induced by the projection from Kahn-Quillen model structure. Okay, so this was a couple of observations, and now let's give another characterization of Kahn-Quillen model structure, which will be useful in our proof of existence of contravariant model structure. So first, let's consider an interval object, which is a nerve of the following two-object groupoid. Well, this groupoid is contractible, and we have an interval object. So it is a Kahn complex, and so it is a Kahn complex because it's an infinity groupoid, and all morphisms are invertible. And it is contractible because the unique map from J prime to the point is a simplicial of homotopical. Okay, so what that means? Well, that means that if we take the projection of the following direct product, it is a trivial vibration. For any simplicial set X. And thus we get an exact cylinder on the category of simplicial sets, which is defined by means of well, the usual construction that we take cylinder to be a product of an interval object with our object. And consider a class of J prime anodyne extensions which contains additionally the inclusions of the form delta lambda and k into delta n for n at least 1 and k in this range. So by lemma 2.1.3, we see that this class of such anodyne extensions that contains these inclusions in fact coincides with the minimal saturated class that contains the following maps. So, well, this is a basic class of maps which defines anodyne extensions. So we take these kinds of unions and map them into a cylinder. So this should work for n at least 0 and epsilon being 0 or 1. And secondly, we should have these inclusions for n at least 1 and k as before. But it turns out that this description is in fact redundant, and we can give a simpler description of this class of J prime anodyne extensions. So position 4.1.7 asserts that in fact this class of J prime anodyne extensions with this additional condition is just a class of right anodyne extensions. Okay, so let's prove this. So first observe that any right anodyne extension is contained in our class. Now we want to prove the converse. So To do this, it is sufficient to prove that any right vibration has the right Lifton property with respect to the generators of the class of our class. Well, because by the small objects argument, the small saturated class is of the form L of R of I, where I is some set of generators. In this case, this set of generators. So it is indeed sufficient to prove that any right vibration has the right Lifton property with respect to the generators. So we want to show that for any I generators, we have a right Lifton property of right vibrations with respect to this map. So observe that in fact I is of the form is of the following form. So here B is a nerve of a small category. It is a small category. And in particular, it means that it is an infinity category. So let P from X to Y be a right vibration. We want to solve a Lifton property of the following form. So we have a Lifton problem of the following form. So we have a monomorphism I here. We have two maps A and B from A to X and B to Y respectively here, and we want to find a lift here. To do this, we first decompose this commutative square into a larger diagram. Which looks like this. So we take a Cartesian square here, and we have the following decomposition of the commutative square above. So Q, since it is a pullback of P, is also a right vibration. And moreover, we know that codomain of Q, KB, is in fact an infinity category. So we reduced our Lifton problem to the case where our right vibration is not just a right vibration, but a right vibration with an infinity categorical codomain. And now we can assume that in fact we have infinity categorical codomain of this map. And what we want to do is we want to prove that such cofibrations have a rate-lifting property with respect to all generators of the class of this anodyne extensions of ours. And we make one more translation of this problem. So what we must prove is that for any p from x to y, where p is a rate vibration, y is an infinity category, the evaluation map at epsilon equal to 0 or 1 is a trivial vibration. So we have a map between internal home objects and simplicial sets from J prime x to this hybrid product. And we want it to be a trivial vibration. However, observe that P is always an isovibration by the following result from section 3, which means that P is a vibration in a real model structure on simplicial sets. So this is another result from section 3. And in particular, that means that it must have the required lifting properties. So since J prime is an infinity groupoid, we have the following identity. For any infinity category C. And that means that we can apply result section 3 which yields the existence of the lift. Okay, so this proposition, well, in fact, it immediately allows us to prove this Gilles theorem on existence of contravariant model structure in this comma category. So proof of theorem 4.1.5. So the theorem now becomes an instant of the construction. From section 2.5 about absolute weak equivalences. Due to this proposition that we just proved. And it means that we can apply a theorem and we can apply the theorem to 4.19 for A equal to this Eulenberg-Zilberg category, which is just a category of simplices of C. And since we have this identification, we proved the theorem about existence and uniqueness of contravariant model structure. Okay, so now let's move on to other corollaries of this proposition. And first, let me introduce the following notion. So assume that we have just some morphism of simplicial sets. Then it is final if for any other simplicial set C and any morphism from B to C, the induced morphism between simplicial sets over C is in fact is a equivalence in contravariant model structure in simplicial sets over C. Okay, so we can now give the following corollary, which characterizes right anodyne extensions and its relation to their relation to final maps. So if we have a monomorphism in simplicial sets, then F is a right anodyne extension if and only if it is a final map. And more generally, a morphism of simplicial sets is final if and only if f can be decomposed as follows. So here P is a trivial vibration and I is a right anodyne extension. Moreover, the class C of final maps is the smallest class in morphisms of simplicial sets such that the following properties are satisfied. So A, C is closed under composition. B, for any pair of composable morphisms F and G, if F and GF both are in C, that means that G is also in C. So it is half of 2 out of 3 properties, so to speak. And finally, the class of right anodyne extensions should sit inside of the C. Well, the proof of this proposition or this corollary is in fact just a direct application of the results about absolute weak equivalences. So let me just write this down. So this immediately follows proposition 2 and 5.3 and 4. So we have another corollary of the previous proposition, which states the following. So assume that we have a pair F and G composable morphisms. Sorry, not just morphisms, but they are both monomorphisms of simplicial sets. And additionally, assume that F is a right anodyne extension, then G is a right anodyne extension if and only if their composite is a right anodyne extension. Well, I think this is pretty clear. And now let's give a sufficient condition for finality of a map of simplicial sets. So, assume that we have a map of simplicial sets. and assume that we have a right vibration like this. Then F is final if non-leaf E turns F into a weak equivalence of contravariant model structure over C. This proposition also follows from the result about absolute weak equivalences. And now let's move on to define mapping spaces in this category of simplicial sets over C. So let F be a simplicial set over C, and let G also be a simplicial set over C. Then we can define mapping space between F and G by means of the following Cartesian square. So we take a map from internal home between F and G into internal home between F and C, and here we take a fiber of this map over precisely over the map PF. So this is the definition of a mapping space between F and G. If G is right vibrant over C, then this mapping space between F and G is a fiber of a right vibration, and hence by proposition 3.4.5, this is a Kahn complex. Okay, so assume that we have an object C small inside this simplicial set C, and denote by H of C the corresponding morphism from the point to C. I'm sorry, not the morphism itself, the image of corresponding morphism. So basically, that's just a simplicial subset generated by C. And the canonical isomorphism between an internal home from the point to x and x induces a canonical isomorphism between the mapping space of C over C from HC to G and the fiber of G over C. Okay, so we have the following proposition. Which implies that if G is fibrant, then in fact any morphism between other arguments induces confibration. So assume that we have some morphism over C, and G is right fibrant, then the induced map between mapping spaces is in fact a confibration. So let's prove this result. First, observe that by the previous remark, both I guess let's call this F, so this is F upper star. Both the domain of F upper star and its codomain are concomplexes. Since they are fibers of right fibrations. And by proposition 3.5.5, it is sufficient to show that F upper star is a right configuration. Additionally, we know that right vibrations, right configurations are stable under base change. And thus we see that since right configurations are stable in the base change, and we know a similar result about internal home spaces, namely proposition 3.4.5. We have Cartesian square of right configurations.
Mm.
So, I'm sorry, maybe it's comprehensive. So we have a Cartesian square like this, and the map here is right configuration. And so we see that the map on the left is also right configuration. Okay, now let me formulate another proposition which relates to the previous one, and it states that if we have a weak equivalence of sequential sets over C in the contravariant model structure, then for any right fibrant target, the map between sequential mapping spaces is in fact an equivalence of infinity groupoids. So we have a weak equivalence in contravariant model structure over C. Then for any right fibrant G, the map F upper star from mapping space over C from F prime to G to mapping space over C from F to G is an equivalence of infinity groupoids. So let me prove this. So analogously to the previous proposition, one sees that for any right fibrant object G, the functor of mapping space into G sends right unitary extensions into trivial vibrations. By propositions 2.4.40 and proposition 4.1.7 that we just proved, we see that this functor is in fact is a left Euclidean functor from this contravariant model structure to the usual Euclidean model structure. We should write those. In particular, this functor preserves weak equivalences between cofibrant objects. However, as we well know, cofibrant objects in this case are just all simplicial sets over C. And hence, the proposition holds. Okay, so now I want to prove a technical result about right anodyne extensions. So assume that we have a non-negative integer and we have an inclusion of a simplicial subset generated by nth vertex into delta n. And I claim that this, in fact, a right anodyne extension. How do we prove it? Well, basically, we just exhibit it as a retract of some well-known right anodyne extension. So assume, define a map from this prism into delta n. So let H be defined by formula epsilon x is mapped either to n epsilon is equal to 1 or x otherwise. So basically what happens, we just collapse one side of the prism the top of the prism into this one vertex, and the bottom of the prism remains the identity map. And so we can identify delta n with this subobject inside of delta 1 times delta n. And hence, we have the following diagram. So here we have this inclusion, and then here we have a map which identifies delta m with this subobject. Here we have an inclusion, and here we have a map H. And so this thing right here is clearly a right anodyne extension. And we exhibited this inclusion as a retract of this right anodyne extension. Okay, so now I want to give an equivalent conditions on a map being a fiber-wise equivalence of simplicial sets over C. So theorem 4.1.16. So assume that we have a map from F to G, and it is in fact not just a morphism over C, but it is a morphism of right fibrant objects over C. Then the following conditions are equivalent. So first off, phi is a weak equivalence in this contravariant model structure. Second, phi is a fiber-wise equivalence. And finally, for any simplicial set over C, the induced map phi lower star from X from the mapping space of XF to mapping space of XG is in fact an equivalence of infinity groupwise. Okay, so yeah, I think I'll be able to cover this. So since this mapping space can be defined as a pullback, sorry, not the mapping space, but since the fiber FC is isomorphic to the mapping space from HC to F, we see that the third assertion implies the second one. Additionally, we have a Cartesian square we have a Cartesian square for dimension spaces. So you remember this one where on one side we had internal forms, and on the other side we had the mapping spaces. So this Cartesian square shows that this Cartesian square shows that this functor of mapping space preserves hence this functor preserves trivial vibrations. And by Ken Brown's lemma, this means that it preserves with equivalences in the subcategory of vibrant objects. And this implies that assertion 1 implies assertion 3. Now, by propositions 4.1, 15, and 14, it follows that for any simplicial set over C, and for any right vibrant object over C, there is an identification of a set of connected components of this simplicial set and the set of homotopy classes from X to F. This is because cylinder over X sent into a path object of a Kahn complex map C from X to F in Kahn-Quillen model structure. So we have this isomorphism between set of path components and homotopy classes from X to F. And by this, we see that condition number 3 implies condition number 1. So now the only thing that remains to prove is that condition number 2 implies condition number 3. So assume that we have a non-negative integer and by preceding lemma and proposition. So by lemma 4.1.15 proposition 4.1.14 for any map from delta n to C, we have a commutative square which looks like this. So the horizontal maps are equivalences of infinity groupoids, and we see that condition number 2 is equivalent to the condition that for any map from delta n to C, the morphism phi over star is an equivalence on infinity groupoids. On the other hand, the functors map C F send colimits in category of simplicial sets over C into limits in simplicial sets, and now it remains to apply a whole bunch of statements to see that the class of simplicial maps simplicial sets over C such that this induced map is an equivalence of infinity groupoids is saturated by monomorphisms. Now we apply corollary 1.10 for Erlenberg-Zilberg category A delta over C to prove that the statement, the assertion number 2 implies the assertion number 3. Okay, so I have 3 more minutes, I guess. So let me just state the final corollary of this theorem. 4.1.17. The class of weak equivalences in contravariant model structure is closed under filtered colimits. Well, I guess I can give a proof. It's very short. So first, what we observe is the fact that right fibrations are closed under filtered colimits. Moreover, fibrant resolution commutes with them. Well, fibrant resolution functor for this model category structure, of course. And therefore, it is sufficient to prove that this class of weak equivalences is closed under filtered colimits only between fibrant objects. And now we can apply the previous theorem to reduce it to the case of fiber-wise weak equivalences. Now, since filtered colimits are exact, they preserve small limits, and that means that they in particular preserve an operation of dative fibers, and this means that we only need to check that weak equivalences between infinity groupoids satisfy this property. But this follows from corollary 3.9.8, and we're done. And this shows that weak equivalences are closed under filtered colimits. Okay, I think that's it for today. Basically, just recounted section 4.1 from Cisinski. I don't know, maybe I went into too much detail and it was somewhat boring. I'm sorry for that. This is the case.
Thank you. So maybe I'll stop recording.